Okay. Hi, everybody. Good evening. It's my pleasure to conduct this event today. We have a very, very interesting guest. So welcome to Naxxatra Sciences. And if you're here for the first time and you're watching our live event, welcome to this community. So we are basically an organization with, we are focusing on reaching good quality scientific content to whoever requires it. We are also a bridge between people who want to pursue research and mentors who want to provide the kind of training and research skills that are very much important today. So we have a bunch of courses that people can take, which are pretty intensive 2 to 3 month courses. We also have collaborative projects for people to work on. So welcome again. And if you are someone who wants to be part of the community, most of our activities are happening on our Discord server, virtual campus. I think it's there in the YouTube description. So if you're on YouTube, please leave your comments and be interactive today. I think you can put down any question you have in your mind and we will try to address most of it. We have about an hour or so. So let me go straight into introducing our guest for the day. He's a very, very well-known, interesting person with a very multidisciplinary character. So his name is Sachin Bharadwaj, and he's currently a second-year graduate PhD student and research assistant in the Department of Mechanical Aerospace Engineering at New York University, USA. He holds an undergrad degree with a gold medal in mechanical engineering from R.V College, which is in Bangalore. And he also has a 4-year graduate level scientific achiever program in theoretical physics from the Center for Fundamental Research and Creative Education, also known as CFRCE, which is also in Bangalore. And he was named the 2019 Rhodes Scholarship finalist from India for the Rhodes Trust, University of Oxford, UK. If some of you in the chat have questions about that and you want to know how he did it and what the Rhodes Scholarship is, maybe you can ask him that towards the end of today's talk. He works and his current interest lies primarily in theoretical and computational aspects of quantum computing and information, fluid dynamics, quantum condensed matter physics, and also certain aspects of quantum foundations. So he enjoys doing interdisciplinary research, combining physics into other fields such as biology and music. He currently explores statistical aspects of turbulent flow physics and develops quantum algorithms to understand nonlinear dynamical systems. He has also been a visiting research student and summer research student recipient from DST Government of India, the Jawaharlal Nehru Center for Advanced Scientific Research. He was also visiting researcher at National Center for Biological Sciences, as well as International Center for Theoretical Scientists. Some of you might know ICTS, Bangalore. He has authored around 6 research papers on various topics, and he has given invited talks and lectures at various international conferences in several countries like USA, Germany, Cambridge, China, etc. He has also given invited lectures at the University of Cambridge and more recently a talk at the American Physical Society Division of Fluid Dynamics. And he was also invited to give a talk at the G.I. Taylor Medal Symposium, USA. He also has a very interesting background because other than physics, he also has excelled in the field of music. So some of you today, either on YouTube or you've joined the Zoom call, you might recognize him. If you don't recognize him, you should probably ask your parents. I'm sure they will, especially if you're in Karnataka. So he's a trained and professional Carnatic vocalist and an actor. So he has participated in more than 5 television reality shows like Saregamapa, Little Champs, and Yede Tumbi Haaduvenu, etc. He has also been a winner and finalist in most of them. He has sung as a playback singer for many movies and shows. So if you have any questions on how you can balance, I guess, a career while also having a very active extracurricular life, he's the perfect person for you to, to answer your questions. He has so far acted in around 6 Kannada movies as lead roles in most of them and more than 4 television serials, with 3 of his movies bagging the Karnataka State Award. He has also been a brand ambassador and model for several fashion brands during his earlier years, and he has performed and given more than 70 to 80 concerts and shows across India and other countries as well. So you can see that he's a person of very varied skills and achievements, and it's an honor to have him here. But I also think it was really nice of him to say yes and come as a guest in today's event. Basically, if you're new to Naxxatra, we are having a 4-day quantum mechanics workshop, and this event is part of the workshop. So feel free to ask us any questions about that as well. And without much delay, we will head straight into the program. Welcome, Sachin.
Thank you so much for that introduction. And thanks a lot, Sitara, for inviting me to this. And thank you, Naxxatra, for giving me this platform to share some things with you today. I'll try to keep things coherent, interesting, and dynamic through the next 1 hour or so. Very excited. I see that we have a very diverse audience and a very enthusiastic audience with us. So yes, let's go to the talk directly. So I ask you to be dynamic, maybe in the chat box or whatever. If you have any questions, feel free to ask in between. Preferably in slots of 10-15 after 10-15 minutes. That would be good. And I think so that I know if what I'm telling is coherent and it's kind of making sense, and that would be really great. Okay, so let me share my screen. So is everybody able to see the?
Yeah, it's visible.
PPT? Okay, great. So yes, so as you might have already seen from the title of the talk, the idea was to share certain aspects of quantum mechanics, both fundamental and applied, and to see how we can apply quantum mechanics and see it in action. So I thought of choosing 2 interesting topics for today. One is a brief overview or maybe a more applied overview of quantum mechanics and quantum computing. And another thing would be to talk about entanglement in general. So I'll start with entanglement. I'll start with it and try to explain certain basic aspects of entanglement and what it means physically. I'll try to keep the discussion mathematically minimum today because I want to concentrate more on the physical aspects that differentiates quantum mechanics fundamentally from classical mechanics. And so there are 2 topics, as you can see here. One is entanglement, and you see a long hanging machine here, which is a quantum computer, and you see a fluid flow on the right side, which is a jet. So I will talk a little about how one can use quantum mechanics and eventually in quantum computing to study a very ubiquitous system such as a fluid mechanical system, which we see every day, and how we can use quantum computers to understand fluid dynamical systems and classical systems in general. So for the first part of entanglement, I'll try to switch a little between my PPT and I'll write some things because I think I need to write certain things. So the PPT part of entanglement might be a little lousy, so excuse me for that, but I'll be trying to juggle between the 2. So yes. Let me start from. Great. So with a brief introduction, So what is quantum? So people have this question all the time. What is quantum in general? And most of you here who have connected on the Zoom, I think you're already going through the workshop at Naxxatra, and you have learned some basic things about quantum mechanics in general. So I'd like to address this issue or this question in a more, I would say, with the inspiration of Lev Landau, who was an amazing physicist who had very deep insights about physics in general. So the Landau inspiration is as follows. The first very important thing that differentiates or that one needs to know is the difference between accuracy and precision. So accuracy and precision are like two very important things that one needs to understand before diving into quantum mechanics. The reason is as follows. For example, if you have a dartboard and you throw darts at the bullseye, there are two kinds of scenarios. One is where, say, if I have three darts and all the three darts after I hit are separated from each other, but are all near the bullseye. This is one. The other is there are three darts all very close to each other, but may not be very close to the bullseye. So the second is precision, that is repeatability in measurements. While being as close to the required value is being accurate. So the main problem in quantum mechanics arises from the concept of measurements. So there are two questions. So the question is, do you want your measurements in general, like even simple measurements like a thermometer, to be precise or to be accurate? So accuracy is important, but the reliability of the machine being precise is a tad bit more important. So the key difference between classical measurements or apparatus and quantum measurements is in this. So what is the accuracy that we need and how precisely can we do the measurements? From which we get the Heisenberg's uncertainty principle, which you might know. So we all know, we have lived in the classical world. We feel it, we understand it, we have an intuition about it. Now the question is, how do I go from the classical world to the quantum world? So there are these important key things that we usually miss while one studies quantum mechanics. Either we study classical mechanics fully or we study quantum mechanics fully, but there are certain aspects in between. So the big question, which is still unanswered, is where to draw the line between classical physics and quantum physics. Like, how do I put my foot down and say that, yes, this is classical and this is quantum? Or is there a world that exists in between the two, which is what is called as a semi-classical physics? So where even things like Planck's constant, when normalized with correct energy values, could be taken as a limit, h cross tending to zero, h bar tending to zero. So what would that mean? And things like geometric optics or Fermat's principle. So these things are certain. I wouldn't go very deep into this, but I thought it is very important to talk about all of these things, or at least mention a few things, so that you can go back and look at these concepts a little, so that you know that there exists a world between the classical and the quantum world, which is very interesting in itself and key to understanding the core of quantum mechanics. So maybe I'll skip this. And so, yes. So how did all of this start? Like thinking about quantum mechanics and asking questions such as how is it fundamentally different from classical physics, etc. So the first thing was that there was an urge in the physical community to understand how one can transition from a classical world to a quantum world. So there were people observed classical phenomena, people observed quantum phenomena separately, but didn't know how these two things could be reached from one to the other. So there was this fundamental frustration going on. Einstein and his friends, Podolsky and Rosen, had some fundamental questions about quantum mechanics, which they didn't agree with, which I will in some time explain it to you. People also did see experimental evidences of a quantum mechanical phenomena called entanglement, which I'll talk about. And Einstein asked a question which he wanted to understand: what is reality and localism, which I will also talk about. And they also wanted to know if eventually that if at all entanglement is possible, is teleportation possible? So there were these fundamental curiosities and interests that made people go more into entanglement and ask basic questions. So I'll start with this. This was the 1935 EPR paper by Einstein, Podolsky, and Rosen. They made a strong claim, or they intended to make a strong claim, that quantum mechanics is not a complete theory. Yes, so this is quite a big claim. So maybe I'll start explaining a little about it. So I will stop sharing this and I will rather go on to writing certain things. Is my writing pad visible?
Yeah, we can see.
Great. Okay, so so coming to entanglement directly. So entanglement is one physical phenomena which gives you the stark difference that separates classical physics from quantum physics. So in classical physics, we have rules that talk about measurement. For example, if you want to measure the length of an object or the mass of an object or whatever, of any physical quantity, the measurement itself, the value that I get out of the measurement of the physical quantity, is independent of the act of measurement. That is, the act of measuring something won't change the physical observable. Oops. So first things is, in classical mechanics, act of measurement doesn't affect the observable. But in quantum mechanics, it does. So for example, you might have learned in quantum mechanics that the kind of objects that we deal with are so fundamentally small that measuring certain aspects of the object changes its very state. For example, if I have a small electron sitting here and I want to see it, right? As simple as this. So if I have to see it, there must be a light ray that hits this and then goes to my eye, right? So the act of seeing is a measurement. But note, when this ray of light comes and hits this electron, what happens is, as this hits the electron, this electron state is perturbed a little. I'm trying to draw a very hand-wavy explanation to this. And you see something else, right? So there is some kind of inherent uncertainty here. This concept is actually more mathematically rigorous, but I just want to give an insight into what is happening. So now almost all concepts in quantum mechanics, or rather everything, is based on a probabilistic argument. But Einstein, on the other hand, thought about something like this. So instead, if there is a tennis ball that is sitting and you want to see the tennis ball, right? Suppose I close my eyes and don't see the tennis ball. So the thing is, if I draw an XYZ coordinate system, right? This tennis ball has a specific XYZ coordinate irrespective of whether I see it or not, right? So whether I see it or not, the XYZ has a certain value. So XYZ, these are certain values. So Einstein called these objects, which have certain eigenvalues for physical observables, it might be position, velocity, whatever, which is independent of measurements, as elements of reality. He called these elements of reality whose values doesn't depend on measurement, and they have certain values. But now, if you look back at the quantum mechanics that we have learned, you see that everything is probabilistic. So Einstein and his friends were like, okay, so quantum mechanics doesn't allow for elements of reality to be a part of it. So the essential argument that they wanted to make was that since quantum mechanics is not allowing elements of reality, it cannot be a complete physical theory. And they wanted to prove that quantum mechanics is wrong in certain sense because it does not accommodate elements of reality. So the argument, this was the essence of the argument that they did, but there is a more mathematical formulation of this, which I will talk about it now. So first, let's see mathematically what entanglement actually means. So if I have a quantum object, say an electron or any quantum object, every quantum object is represented as a wave function, or mathematically as a wave vector, which is represented, for example, as a ket psi, which is a vector in a complex Hilbert space. Complex Hilbert space. So this wave vector or a wave function is basically, if you have a complex wave, a complex vector space, which is say C2, it is a unit vector psi, which is somewhere in this space, right? So now, if I have more than two objects, but okay, so before that, say the wave vector for a two-level system, for example, an electron that is in a proton atom that is in a hydrogen atom, hydrogen ion, you either have a zero state or you have a one state, right? It's either spin up or spin down, for example. In quantum mechanics, by the rule of superposition, we know that psi can be written as a vector superposition of 0 and 1, right? It can exist in both the states at the same time with corresponding probability amplitudes. But when I have, for example, two objects, could anybody tell me, for example, if psi1 is for object 1 and psi2 is for object 2, what is the wave function of the composite object? Any guesses?
Multiplication of both the kits.
Perfect. So this is rather a very special multiplication, which is psi1 tensor producted with psi2. So note one thing, that two objects, if I have psi1 and psi2, it cannot be psi1 plus psi2 with whatever alpha or beta, because this would mean that there exists a probability alpha square for psi1 to exist, and there exists a probability beta square for psi2 to exist, but which is not true. Psi1 and psi2 both exist. They both exist in the box that we have taken. So this is the ideal explanation for this. So what happened was that in general, most of the objects could be written as psi1 cross psi2. So now, for example, if there is one object like this, which is 0, and another object 1, we can write it as 0, 1. So let us take an example such as this. It is a 2 quantum object space because this is in a Hilbert space times 2. There are 2 Hilbert space tensor producted here, as you can see. But now, is it possible for me to write this object as a product of some alpha times beta? Is this possible? Sadly, you cannot do this. Still, it is a composite psi of 2 objects can't be written as a tensor product. So mathematically, people defined this psi in this form as an entangled state. So this is an entangled state. That is, if you cannot write an object, a wave function, in terms of a product state of 2 fundamental wave functions, you call that an entangled state. So this is a mathematical notion, a very, very crude mathematical notion of what entanglement is. But it is essential for us to develop a bit more on the physical intuition, which is what is my intention here. So, so far, any questions or any doubts or anything, you can ask me anything. If you want me to make it a little more pedagogic, or if you want me to go a little more slow or something like that.
Is there any limit difference between a quantum particle and a classical object, either in terms of mass or speed? Where do you draw the line that below this is the quantum particle? It will have a quantum behavior.
A very, very interesting question. I mean, it's a very important question as well. So drawing the line is firstly is an unanswered question, even till now. Even philosophers or quantum foundational researchers still are struggling to answer that question. But one thing to note is a quantum phenomena can even happen at macroscopic scales. If I fill an entire room with a quantum fluid, it might have a humongous mass, but it still shows quantum phenomena, or it behaves like a quantum object. So the point where quantum mechanics becomes more apparent or becomes more important is when the act of measurements starts taking an important toll on the eigenvalues of the system. That is where we need to draw the line between quantum mechanics and classical mechanics. But that line is blurred. But that line is certainly blurred because the choice of accuracy is always arbitrary, right? So, but quantum mechanical phenomena becomes more apparent when the effects of measurements becomes more important. So a very, very good question there. So going on, let me talk a little bit about, yes. So what happened was that the way Einstein and his friends, the EPR paper, how they tried to do it was by using the concept of something called as anticorrelation. So the thing was, suppose let me take a state such as this. This is a spin singlet. Sorry. Again, it's hard here to write it as a producted state, tensor producted state. We can show that this is. So if I take the fundamental spins, that is the Pauli matrices, if you know, which can be sigma x, sigma y, sigma z, and the identity matrix. If I take any arbitrary vector v and try to measure the vector v along each of these directions, that is basically I do v dot sigma, we see that each of these measurements have only two eigenvalues, which is either +1 or -1. So, but every time I do this on this object, if for the first object, observe that there are two objects here. If I get an eigenvalue +1, for the second object, I always get a -1. So there is something called as anti-correlation. So how is that happening? So the way it is happening is that every time I measure the first half of this object, I get an eigenvalue +1. But the very moment I get the value +1, I get the value -1 for the very next measurement. That means the second measurement was almost instantly known that but it's the vice versa. If I get a -1 here, I get a +1 here. for the eigenvalues. So Einstein told, okay, so if I measure one object, so the eigenvalue of the second object was almost instantly known even before I measured it, right? So this is exactly like the elements of reality that he was measuring, just like the tennis ball that we looked at. So he told, yeah, I mean, this would also mean that there exists elements of reality, and quantum mechanics doesn't allow for this, and quantum mechanics is not a complete theory. So how he went on with this was that, so they did a small experiment. So Charlie prepares two objects that are entangled. And then he gives one to Alice and one to Bob. That is, if we have a state such as this, he gives the first object to Alice and the second object to Bob, right? And then say Alice has two physical things, like maybe mass and momentum or velocity, and any two physical observables, for example, Q and R, which can take eigenvalues plus or minus 1, R plus or minus 1. Similarly, Bob has something with S and T, two physical observables that he wants to measure, plus or minus 1, plus or minus 1. So in order to see this, since Einstein told that elements of reality doesn't exist, and in fact, I mean, elements of reality exist, but quantum mechanics doesn't account for this, and this is not a complete theory. And in fact, this paper ruled for almost 30 years. And 30 years later, this guy called Bell comes up and does this very, very simple calculation that I'm trying to show now, which is just based on classical physics or mathematics. So if I have two observables such as this, QR and ST, let us take an object something like QS plus RT plus RS minus QT. Let me compute a function f, which is something like this. I see that it is Q plus R times S and R minus Q times T. You can see that because all of these four values takes plus or minus 1, it's either QR plus S is equal to 0 or R minus Q times T is equal to 0, right? Because if this R is minus 1, then the other is plus. Here also R is minus 1 and the other should be plus 1, minus 1. So either this is 0 or this goes to 0, right? So now one notes that this entire thing, if either one of this is 0, this entire thing is either plus or minus 2, right? Because this will be 1 plus 1 and this will be 1 and this will be 2, or 1 minus of minus 1, 2 times 1 will be 2, or it will be the minus of it if this t is minus 1. So this object, which is gotten off of the values that these four physical observables Q, R, S, T can take, is plus or minus 2. So now if I take the expectation value of this object, Qs plus Rs plus Rt minus Qt, which is basically, I can write it as this is equal to the probability of measuring QRST, that is, times the values that I get, Rs plus Rt minus Qt. When I do this, I know this guy is 2, at most 2, so I can convert this into an inequality, summation of probabilities times 2. and I know always this is 1. So this is always less than or equal to 2, this entire function, right? This function is called as the Bell's inequality. Here, I did not use any quantum mechanics whatsoever. I just used very simple classical probabilities. But then later, what we can do is we can choose our good old friend, that is 0, 1 minus 1, 0 by root 2. And if I choose a very specific operators for the physical observables, such as this, which you don't have to worry about here, I see that if I plug these into these values and use quantum mechanics instead, I get 2 root 2. But see that this guy is basically violating this inequality, right? So is basically violating this inequality. So which means quantum mechanics violates Bell's inequality. So which means there was some assumption that we made. If quantum mechanics is the real nature that we think about, then there is something fundamentally different here that we assumed wrong while doing the classical analysis, which was not supposed to be done, right? So one was the concept of locality. The other was the concept of realism, right? So one is we assumed that they might have certain eigenvalues. And the other thing was measurement of one object doesn't affect the values of measurement of the other object. So that's the locality and realism. But even today in quantum mechanics, people do believe that locality and either one of these should be dropped, but people don't know which to drop. Is the world local or is the world real? I mean, in the sense, is it realism? So, but nature is not locally realistic. It's either one of them. This is what entanglement shows, that the world is not fundamentally classical to a certain degree, right? So this is one very important thing, the violation of Bell's inequality, that sets quantum mechanics apart from the classical physics. Yes. So now I think I will go on to one interesting experiment, which I will also demonstrate. Possibly I'll stop sharing this. So last thing that I want to talk about here is how I can use this concept of a small tail that one can use quantum entanglement is to do quantum teleportation. So what is quantum teleportation basically? Is basically transferring qubits, that is basically any quantum object, through a quantum channel to another point in space, right? So the story is as it goes. Alice and Bob met a long time ago, and they fall in love. When they meet, they created an entanglement pair, which I showed. It's either 0, 0 and 1, 1, which cannot be separated, as a token of love. And each one took one part of it away, and they went away for a few years, and they eventually break up and they go away to different parts in the world. Now, Alice, after many years, she wants to come back to Bob, but she doesn't know where he is. But she still has the EPR pair with her. That is the one half of the entanglement pair. Now, let us look at what situation that Alice is facing. So, one, she doesn't know where Bob is. Two, she can't measure her qubit. Like she can't see her qubit, because if she sees her pair, it will collapse because of the rules of quantum mechanics. She can't make a she can't also make a copy of the qubit she has, or the entanglement pair she has, because in order to copy, you need to measure it or like interact with it, for which you cannot copy it. And he is far, far away in space, and we don't know where he is. But now the question is, can she still send the information that she wants, or call him, or whatever, even if they're so far away? The answer is yes. So the quantum this is where quantum teleportation comes to rescue. So you don't have to worry about what this figure is, but this figure represents a quantum circuit. Just like a classical electronic circuit, this is a quantum circuit, which exactly does what we want. That is, basically create an entangled pair, separate Alice and Bob far away, and then I want to send a bit of information from Alice to Bob. Now, I'll show you that here. So this is a code that was written on an actual quantum computing device at IBM Q, which is on IBM. So these are actual quantum objects. And I generated exactly the circuit which you saw here. And finally, you see that the 0, 0 and 1, 1 state, which we wanted, was exactly created here with 50% probabilities. I think this is something extremely wonderful, because these were real quantum objects, and we were able to entangle 2 electrons. And these are the actual results that came out of a quantum computing device. So imagine something as abstract as I explained what Einstein talked about is actually happening in real time. So Alice can use the circuit that I showed just now to send a bit of information across a quantum channel to Bob, and he will know that what Alice wanted to send just by measuring his own object. And this is completely possible as shown on this plot here. So this is something very interesting. So now I think if you have any questions, I can stop here and move on to the last part. I mean, the quantum computing part.
Hello.
Yes.
How do we entangle 2 electrons?
How do we?
Entangle 2 electrons.
So creating entanglement could be done in several ways. The simplest is just by interacting them. 2 electrons could also be entanglement, probably, if, for instance, when they are generated out of a beta decay of a nuclear process.
So when we say 2 electrons are entangled, what's actually happening?
Yes. So when two electrons are entangled, it means that there are 2 objects which are interacting in space, but these 2 objects form a composite object together. So you cannot treat them independently. So you do something to the first object, there is a change in eigenvalues for the second object as well. So that is what is called entanglement. So in mathematically, when I showed, it meant that you cannot write the wave function of an object as a product of 2 objects. So which essentially means that when 2 objects are entangled, no matter how far they are in space, the fundamental wave function of the object is a composite object. They should be treated as a composite object, right? And any perturbation to one object will certainly cause certain aspects to change for the second object. This is what entanglement means.
It's kind of weird connection between them.
Yes, it is called spooky action at
Yes.
right? Great.
So how does this Einstein said that it violates special theory of relativity. So
Yeah. So now what happened was we saw the Q, R, S, and T, right? The values that Alice and Bob measure.
yes.
What they do is they measure their own each halves at exactly the same instant of time, right? Alice measures what she has exactly at time t is equal to t, and Bob also does the same thing. But now the point is, if Alice gets a value +1, Bob will get a value -1. Now the problem is, Alice will know the value of Bob's measurement the very instant she measures hers. If Alice sees that, oh, she has a +1 in her measurement, she knows that Bob will have -1 with him. That is the reason we conduct this experiment exactly at the same time, because we don't want any causal connections between the two. Because if there is a delay between the two measurements, Alice has some time to send the information to Bob that, hey, look, I got a +1. Did you get a -1, right? So what happened was, even when they did the measurement exactly at the same time, the values were known. If at all Alice had to communicate this instantly, that means the message should have been sent way faster than the speed of light, right? So this is exactly what Einstein thought. He thought, oh yes, if Bob already knows it's -1, even before Alice says it, maybe she's able to send information to Bob faster than speed of light. In fact, there was a point in time where Einstein wanted to prove himself wrong. Like, he had that evil joy that he wanted to feel that, oh, my special theory of relativities might be wrong. But sadly, he was proved wrong later by Bell when things violated Bell's inequality.
Okay. So particles, when they are produced, they can be entangled. Is that right?
Yes. So basically, they should have some kind of an interaction which makes things entangled.
Okay. Now, I am genetically connected to my parents. Does that mean I'm entangled with them also? Like my particles are entangled with their particles?
Interesting question. So the word entanglement here has a more specific meaning. So when I say two objects are entangled, it means that the very state which they are in. For example, if I want to write down the complete description of object A, I need, say, some set of sentences which I can use to describe object A, and similarly object B. If those two definitions cannot be separated of each other, only then they are entangled. That is, you cannot write as a producted space. For example, you and your parents might have commonality in traits or commonality in whatever you do, but you are an independent person by yourself with a complete description of yourself, right? So that is what is slightly different.
Right. Okay.
Sachin, since you're giving a conceptual description of that particular question, could you maybe emphasize on like the experimental side of it, like in laboratory conditions, what does it mean to have achieved entanglement? So maybe that gives us, that'll give us a better view of what it means for two particles to be actually entangled.
So, yes, so entanglement of two particles is basically, without going into too much of details, it's basically a kind of interaction between two particles. It can, for example, you can generate photonic entanglements when you have, single photon generators, for example, that exists. There are single photon generators at RRI. So the single photon generators can generate single photons, and the way they are generated, they first interact in a certain way, and the physical observables of these can be observed later by optical measurements that they're entangled, the way we can do that. So that is one of it. Or even like the beta decay process is an example for entanglement. So whenever there is an entanglement, but note, for example, the way we wrote an entangled pair, right, in the mathematical aspect, it is basically like writing a Slater determinant. If you know what a Slater determinant is, like you can take any two objects, and if I can write it as a Slater determinant, you can then write it as an entanglement pair. But physically, what it means, as you asked, is basically they have interacted before, they have a history of interaction, and now they can be separated as far as apart. For example, there was this recent experiment between, say, Delinga and Li Jiang, where two electrons separated miles apart, which were entangled. So first they were interacted before, and they were miles apart now. And now they saw that a small change in perturbation of this electron sitting in one part of the city when changed the state of the other electron sitting somewhere else. So this is true entanglement. And you can also break entanglement, like by thermal excitations and things like that. You can always break entanglement and make them independent. That is also possible. So, yeah.
Yeah, thanks for bringing up RRI. I think those of you who want to like know a bit more, they have an amazing lab, and I think you need extremely cold conditions to do certain experiments as well. So the experimental side of it is pretty interesting. Just to again comment on the previous question, again, I'm getting a lot of those questions. So you're saying that when Alice, she finds out that it's +1, then Bob automatically knows that it is -1. So people's questions are basically about information exchange. So doesn't information take time to travel? So how do you say that this is not a violation of that? Basically of the principle that it should travel at the speed of light.
Very true. So the point is, if you have to send information physically, it is only possible via a classical channel, right? If you want to send a bit of data to any point, you need, for example, an optic fiber or wireless connection or whatever, which happens classically, a classical channel, which will always happen at the speed of light, right? At most. But in terms of entanglement here, the value that Bob sees is independent of whether Alice talks to Bob or not. That is the key difference. If Alice can send a bit of information, that is different. So that was the very reason we said Alice and Bob both see their particles exactly at the same time, because I'm not giving Alice any time to send any information to Bob.
Okay.
Even before that, if Bob knows or Alice knows what Bob will have, it is not because they communicated, but it was because of the inherent anti-correlation between the two objects. Okay. So this is exactly the same confusion Einstein had, or like the kind of thought that Einstein had. Yeah.
Got it. So to put it simply, naively, there is no information exchange in some sense.
As far as anti-correlation
is.
Right. But she can always send a bit of information to Bob. So so the way teleportation will happen is the anti-correlation part of it has already taken place when Alice measures her part of the entanglement pair. What she does later is that once she knows and once she has seen the measurement, she sees, okay, I see this value, and I want to say that to Bob, for example. She can then just pick her phone up and call Bob, or maybe something like that, send some kind of information to him, and he can verify it later. So that is how, and he can measure his object in the right basis, so that he can extract the exact information that Alice wanted to say. Yeah.
A theoretical question, will entanglement work in absolute zero?
So most of the concepts that we are talking here are mostly absolute zero, because when I say, because finite temperature effects can actually break entanglement because of any thermal excitations. But here, when I talked about entanglement, I never talked anything about temperature. So it is basically at the very physical nature of the electron itself, even at 0 Kelvin. So it does not have to do anything with 0 point oscillations, for instance.
Cool. So we do have a bunch of other slightly more conceptual questions, and I think it will make sense to take them in the last so that we don't divert from the topic. So maybe you can continue and we'll come back to those.
Yes. Okay. So now I want to try to, so since I gave a little intro to quantum computing a bit, we saw that something as fundamental as a concept such as entanglement could be done exactly on a quantum computer. I showed you the code that I ran on an actual quantum device on IBM Q. Now, let us look at how one can use quantum mechanics in general to understand other physical, like classical physical systems that we see around us. So let me choose the field, or maybe the physical system of fluids, for instance. Fluids are something very common that we see almost every day. It might be the air we breathe, it might be water in your tap, etc. People have been doing fluid mechanics research for quite some time. It's been years, it's been thousands of years maybe. So fluid mechanics research so far has taken place in terms of experiments, or in terms of theory, or in terms of computation, right? These are three key modes of research to understand fluid mechanics. Now let us concentrate a bit more on computation. So with the advent of high performance computing, really large supercomputer and direct numerical simulations, we have been able to understand fluid mechanics very well. I mean, we know a lot of things about fluids in general, or turbulent flows in general. So we in fact started out with scales of computers, like in the 1950s, from scales such as deca, and then we went to giga scales, and then we went to tera scales, and then we went to petascales, and now we are in the age of an exascale machine, which is quite a massive computer, right? And along with the introduction of GPUs, along with CPUs, we have been able to do extremely wonderful and high resolution computational experiments and simulations. Now the question is, what next? So there is a recent paper that I wrote with my advisor here recently, which you can take a look about, concepts about quantum computing and fluid dynamics if you're interested, which is on arXiv to be published soon. So now if you think about what are the next steps, so we have a huge supercomputer now, and we want to do better measurements. So what we are trying to do every single time in any field is that we are trying to build better and better measurement devices. It might be microscopes, it might be thermometers, it might be computers, so that we get better and better accurate and precise measurements. But now we try to keep going forward, even in terms of computers. We try to build bigger machines to understand, to do CFD simulations much, much better. But there are certain problems. Can we manufacture smaller? How hard is it manufacturing smaller transistors? What about the quantum effects at such scales? Because if we manufacture smaller and smaller transistors, we are going to eventually reach a scale where quantum effect starts becoming dominant. How long would we take to develop those machines? And as you make computers more with higher frequencies, temperature problems arise. And are new algorithms the only key? What about the massive data sets that we will get from such huge machines? And even if we build bigger machines, can we actually solve all the questions that we have at hand? So what one needs to realize is that we need a completely different kind of computing. We need a completely different kind of computing by itself, which is a paradigm shift. So here we now use the rules of quantum mechanics. The computers that we have been using so far, the classical, the laptop that I'm using right now, use the rules of classical mechanics in general to function. So the notion of computation itself. But when one introduces the rules of quantum mechanics to compute, to measure, we get a new form of computing called as quantum computing. So in quantum computing, as opposed to classical computers, we manipulate quantum objects such as electrons or superconducting transmons or things like that to basically do simple computation such as addition, multiplication, subtraction, whatever, right? All simple mathematical and logical operations. But since now we are using the role of the rules of quantum mechanics, this entire form of computing is very, very physical. That is, I'm using actual physical objects such as electrons, quantum objects, simultaneously doing theory on it and then computation and experiments all at the same time. I think it's one of the most physical ways of computing ever. So currently, as of 2020, we are in this era called as the NISQ era, noisy intermediate scale quantum era, where we have, say, a few tens or hundreds of qubits. We'll talk about what qubits are. Basically, think of them for now, for a slide or two, as they're like classical bits, like bit of information, but they're a special kind of bit. But we have, like, say, hundreds or maybe 1,000, which is basically like having, we are in the 1950s of computing, right? And they're noisy. Like one of you asked, we can't achieve 0 Kelvin in any way. So we always have finite temperature effects, and we need to, there is noises that are induced. And this is already being used in many fields such as finance, medicine, quantum chemistry, optimization methods, and cryptography. And I think this era of quantum computing is going to bring a huge revolution to what we know today of computing and how well we can do computing. What me and my advisor in our group, we plan to do is try to understand fluid mechanical problems, but quantum mechanically. That is, basically we set up computational fluid dynamics problems, which people have been doing so far, that is CFD. But then what we do is we use the rules of quantum mechanics to compute instead. So this is the new field called as QCFD, that is quantum computation of fluid dynamics, which we have been working on now. So what is quantum computation? It is a form of computing which uses the rules of quantum mechanics, as I said. It manipulates, just like we manipulate bits of information, here we manipulate bits called as qubits. These bear information. And how do we manipulate them? We use by using quantum algorithms, which are basically made of quantum gates and circuits. Now, there's a lot of quantum word drop going on here. So I think it's good to look a little more detailedly into what these things are. So what are qubits? They're exactly like a classical bit, but with an extra quantum jazz, right? So a classical bit is something like this, right? It's either on or off. It's one of this, right? But when I invoke the rules of quantum mechanics, I can use the rules of vector superpositions of states, right? So it can be 0 or 1 at the same time, but when you actually measure them, they're either 0 or 1, right? They're actual, and these are actual physical systems, as we know, that there might be electrons or superconducting transmons, etc., or photons. Mathematically, as I already told, they are wave functions in a Hilbert space. You can always write them as a vector superposition of 0 and 1. Geometrically, you can also look at them as a unit vector on a unit sphere called as the Bloch sphere, where the two possible states 0 and 1 are on the 2 poles. And mathematically, you can write them down as this, using the 3 angles of the spherical coordinate system. For example, you can take a spin of an object. It can be spin up or spin down. Quantum mechanically, they can be spin up and spin down at the same time with probability amplitudes 0.8 and 0.6, which means 64% probability and 36% probability of it being up or down, right? Now, if you ask what are the physical objects that can do this and what are the quantum computers that are being used right now, there are different objects. For example, it can be photons, it can be nuclear magnetic resonance, NMR, it can be cold atoms, it can be Majorana fermions, superconducting transbonds, and so on. There are several quantum objects that one can use to use them as qubits. So qubits are basically wave functions of a quantum object, right? Now, what are quantum gates? Just like classical gates. But these quantum gates are basically unitary operators. These, when I say unitary, that is U is equal to U dagger. That is, it's the U dagger inverse. So these unitary operators, and they're reversible. You can always get back the state by applying the inverse operation. So these are essentially operators which change or which rotate the unit vector on this block sphere, as you see. So they basically cause rotation. So that is, if you have a block sphere like this, you make it go through a quantum gate, it just rotates, right? There are many gates. There are X, Y, Z, Hadamard, Toffoli, phase gate, and so many other gates. Just like we have different gates like AND, NOT, OR, NOR, XOR gates in classical computing. And we also know that NAND gates are universal gates, right? Similarly, we have a set of gates in quantum computing, which are also universal and can emulate any other gates with arbitrary accuracy. A good review of all these concepts can be found in Nielsen and Chuang textbook. It's a wonderful textbook. Finally, what are quantum circuits? They're basically an interconnection of these quantum gates in a very specific manner, which will do the job that we want and compute the way we want it to. For example, let's look at something very familiar with. Let's go back to our basics. Let's take a NOT gate. We all are familiar with a NOT gate circuit. What does it take? It takes 0 to 1 and 1 to, it basically flips the state, right? The same thing in quantum mechanics is done by the Pauli X operator, which looks somewhat like this. So if you have a ket 0, it takes it to ket 1 and ket 1 to ket 0. Now the quantum circuit which does this is shown here, right? X is the gate, and then X is the Pauli X operator, Q0 is the qubit, and this is the measurement operator, and then you have a classical register here which can store whatever you measure. So suppose I create a state which is a superposition of 0 and 1 with probabilities as shown here, 0.592 and 0.408. If I input this initial state into the circuit as shown here, I get something like this, which is exactly flipping the states that we had. So the probabilities of 0 has been transferred to 1 and probability of 1 has been transferred to 0, which is exactly what we wanted. And this is like a hello world program on a quantum computer, which is using the rules of quantum mechanics. This, in fact, was a code that I ran on an IBM Q machine. And this is an actual quantum object doing this for us. Let me skip this part. But anyways, so now you might ask, what are the things that one can do using quantum computing? Can we compute dynamical systems that we have been doing using computers so far? Yes, we can try to understand quantum systems itself. We can try to understand classical systems. We can also write new algorithms in the field of algorithmic research as well. So in quantum systems, we can understand lattice systems and continuum systems. When I say lattice systems, if you are familiar with things like Hubbard model, spin chains, and lattice gas, we can understand those. In terms of continuum systems, it can be quantum fluids, Fermi liquids, Bose-Einstein condensates, etc. On the classical aspect, also we can study lattice and continuum systems. On lattice-based systems, it can be things like crystal lattices, Ising models, or any lattice-based object that we know of. And continuum systems that I study, something like Navier-Stokes, classical field theory, etc. On the quantum algorithm side, you can also start developing algorithms, only algorithms, independent of the physics. For example, ODE-PD solvers, optimization methods, eigenvalue solvers, or interpolation techniques. by using the rules of quantum mechanics. And we see that when we use the rules of quantum mechanics, most of these algorithms have exponentially high, either quadratic or super polynomial or exponentially high speed up in terms of computational complexity. And all of this can also be done in terms of quantum simulations, which I will talk about. So before I go into a little more detail, if you have any questions here or basic interests about this, you could ask me, and I will go to the last few parts of this talk, and then we can continue.
How to add 1 + 1 = 2 in quantum computer?
Great. So let me see if I can change this to.
We have to use the quantum gates, right, for that.
Yes. So we need to use quantum gates. Basically, the idea would be to convert, for example, 1 and 1, for instance, to the binary format, right? Which is, if you have a two-bit state, it is 0, 1 and 0, 1.
Yes.
And then now I need to add this so that I get a state 2, which is basically 1, 0.
1, 0, yes, 1, 0.
Right? So the idea is you create a 2-qubit state, or 0 and 1 state, and you have another bit which has a 0 and 1 state. So you make this, there is an algorithm called as a quantum adder, just like we have half adders and full adders.
Full adders, yes.
Just like that, we have adders in quantum computers as well, where we manipulate bits. So basically what we do, we take a 0 bit, we try to add a unitary operator and try to rotate it to 1 state, for instance, right? So even in addition, we basically do that. So we basically rotate objects to in a certain fashion for addition, and rotate objects in a certain fashion for subtraction, so on, so that the final state, after applying 2 or 3 few gates, we will get 2 as the answer. So we make systems end up in a state where they are added into numbers.
The numbers, the final answer will be probabilistic, right? In probability.
Yes, so true, very true. So, but there are ways in which, so any operation that we do, final state will be probabilistic, and you will have to measure the state, right, to know what the values are. So, and we know that the act of measurement is always a problem in quantum mechanics because it induces errors based on the probabilities that the states are superposed in. So there are 2 important things. One is called as quantum amplitude amplification, that is amplifying the probability or success rate of getting the right answer, point number 1. And point number 2 is what is known as quantum state tomography, where we basically take a final state and try to characterize it as accurately as possible. That is, try to go and hit the right answer as much as possible. So we can do this with sufficient accuracy for smaller number of qubits. Any mathematical operation we can do up to 99% accuracy, or 90 more than that, for instance. But on real quantum devices, as you go for higher number of qubits, as you know that there is noise induced in the system, which brings a lot of errors, which is a field by itself called as error correction codes.
Okay, thank you.
Okay, so we have another question from Dwij. So can one find a solution to Navier-Stokes equation using a quantum QM computer?
So, good question. So the solution, what we are trying to do here in a quantum computer is a numerical solution. We are not trying to arrive at an analytic solution. So the problem what we are trying to address here is that we have been trying to use computers to get approximate numerical solutions for the Navier-Stokes PDE, right? But we are not trying to, but what is happening is to get the final solution, or at least to get maximum understanding of Navier-Stokes, we need to have really highly resolved simulations, for which we need humongous computing hours and humongous computer capabilities, which even with the biggest computers we have, we are not able to achieve. So what in QC, what we are trying to do is just that the capability of the computer is many-fold compared to a classical computer. So what we aim at doing is getting still an approximate solution, a numerical solution, but a really, really good one. So that is the idea. So as compared to the solutions we have had in classical computers. But if you want a full form closed solution to the Navier-Stokes, you also need analytic solutions for that, right? So this is a computational approach towards Navier-Stokes. In order to solve the PDE, I don't know. I'm not sure if the solutions what we get would solve the Navier-Stokes, but it would solve Navier-Stokes if we understand at least the dynamics of turbulent flow to a really high extent, at least by whatever approximate solutions we can get.
Right. One more naive question is, how would you explain the benefits of using a quantum computer, and why bother with it at all, compared to the computer systems we already have today?
Yes, I will come to that eventually.
Okay. Cool. Yeah. If anybody else has questions, you can just unmute and ask.
You just told that you can increase the probability of the quantum computing output. But what we understand, the probability function in quantum computing is the uncertainty part. It's not the ignorance part, which is normal in classical mechanics. It is the underlying uncertainty. That's what we understood. How do you understand that? Am I clear?
Could you repeat once again?
You just told to the previous question that you can increase the probability, amplify the probability.
Yes.
But in the quantum world, the probability function is the reflection of the underlying uncertainty. It's not the ignorance. Suppose you're tossing a coin. See, that is a part of ignorance. If you have all the data available, you can find out which side, whether head or tail will come. So it's the ignorance part of the probability. But that is the underlying uncertainty which is in the quantum world. That's what we have been to understand. So
exactly.
If that is the case, how do you increase the probability of the output which you just told?
Very good question. So I'll try to answer this quickly here. So the idea is something like this. So if I have, so for example, what you said was that if I have alpha 0 and beta 1, the probabilities here is alpha square and beta square. This is the fundamental probability that even you talked about right now. When I say amplitude amplification, for example, if for some operation, if 1 is the correct answer, now I want the correct answer to have higher probability than the wrong answer. So that is, say I want beta square to be much, much greater than alpha square. So when I say amplitude amplification, I know that there is a state that exists such as this, but I will make it undergo some amplitude amplification such that it goes into some state alpha prime plus beta prime, such that beta prime squared is much, much greater than alpha prime squared. So what I did was that I increased beta to beta prime so that now when I measure this state, the chances I land on 1 is higher because this is the correct answer. So this is amplitude amplification. This is what I meant. but what you told exactly holds even after I arrive at this state as well. Did I make sense?
Yeah, okay, thank you.
Great.
Right.
So,
Anybody
yes.
else? Okay, I think you can after this also address like the fundamental differences and things like that after this part. We can come to those questions.
So, one important thing was, maybe I'll skip the lattice systems. So continuum systems is what I primarily work on. So you could do a quantum simulation of Schrodinger equation or numerical solutions of the continuum governing equation. So how do you do quantum computing to understand, for example, any continuum classical or quantum system or classical system? One is a method that was proposed by Seth Lloyd, 96, this paper in Science. So the idea is, first we find a fully analytic Hamiltonian or a model Hamiltonian H. And then we write down the corresponding Schrodinger equation, which is this. And then we run a quantum simulation algorithm, which is basically a integration of this equation. So this is one way of understanding. So any system that you want to understand, if you can develop or find out an analytic or a model Hamiltonian, then you can always set things up as a Schrodinger equation and integrate it. And every time step of the evolution, that is, when integrating, can be done in parts by what is known as Lee-Trotter-Suzuki decomposition. On the other hand, you could set it up as a numerical problem. That is, I have an equation that I want to solve, be it Navier-Stokes or Maxwell's equations or whatever it is. And so basically what I would do if I want to solve it on a normal computer, I would do it, for instance, using ODPD solver, right? For example, I would develop a numerical scheme, for example, Runge-Kutta solver or something like that. And I would try to set, or an eigenvalue solver to solve the OD or PD. So the three essential steps would be, first, to load data that we do on a normal computer as well. It can be initial conditions, boundary values, or whatever. Step two would be to set up a quantum algorithm, an algorithm which does what we want, that is, do an ODPD solver. Step three would be quantum state metrology, that is basically extract the data, the final results that we have, and store it to understand the solutions of the problem. So the quantum protocol, what we can choose, for example, I chose is set up a discrete element method. When I use a discrete element method, you can basically set it up as an AX equal to B eigenvalue problem and solve for the, for example, if you want to solve a Poisson flow, you can solve for the pressure and velocity by matrix inversion. So step one is data loading. So how do you load data? So if you were writing a C program or a Python program or whatever, it would just be initializing and declaring a variable. It is int a is equal to something, right? So for example, in quantum computing, if I want to say input 4 values such as this, like I 2 plus I root 2 I and 1, there is one method of loading data which is called amplitude loading, which gives us a state such as this, which is a superposition of a 2-qubit state with these 4 values, right? And 1/3 is the normalization. So what has happened here is that I have loaded these 4 values as the probability amplitudes of the states of superposition that I have, right? And the circuit that does this is shown here, which is on an actual quantum device. And then we see that when I measure the probabilities of the states by doing multiple measurements and experiments, I see that these are the statistics for each of those values. And I see that they're exactly the probabilities that I want. So now I have embedded information, the information that I wanted, onto a quantum device, which is in form of the probability amplitudes of the quantum object. There is another method called a state loading. For example, if you want to load a data such as int a is equal to 10, and that would mean on binary 1010. So this would give us a state. For example, if for this state loading, I load the data directly as the state of the quantum object itself. That is, if you see the third qubit in this setup, it's 1010. So if I know what the state of the third qubit is, it holds the information that I want. So I generally used, for my fluid dynamics simulations, the type 1 kind of amplitude loading for an AX equal to B. And the quantum algorithm that one can use to understand, for example, a Poisson flow, a simple ODE, PD, or a Maxwell's equation to do matrix inversion, AX equal to B, is called as the HHL algorithm. You don't have to worry about what the circuit diagram here is. But note that we need like maybe 4 qubits, like 3 qubits to store some values. In all, maybe a few tens of qubits to store and compute on, say, multiple values of storing data. So for instance, if I have to store 16 values of decimal numbers, it means 16 floating point operations or 16 floating values, which is hundreds of bits or thousands of bits, right? But here I just have a few bits. That is, because I am storing it as a superposition, I can store 2 bits of data at exactly the same time. I don't need 2 separate bits to hold 2 separate information for me, because I can use the rule of quantum vector superposition. Finally, is what I use is called as quantum state tomography. That is basically to measure the final states. But like we saw before, we know that we cannot measure both the states of a superposition, because by rules of quantum mechanics, if you measure one of the states, the other state will collapse to the one of the given states. So one way to go forward is what is known as state tomography. So what I do is I set up a density matrix operator as shown here, which is the outer product of 2 wave functions. And then I set this density matrix, I split it up open in terms of the basic Pauli matrices as shown here. And we know that the expectation value of a matrix or an eigenvalue of X, for example, X Pauli matrix, is the trace of X times the density operator. Now, when I measure the values of X, Y, Z, and I in this corresponding basis, I get the eigenvalues of the observable. So I do multiple measurements and do an averaging, which gives me the expectation value. So I know what is average of X, or the expectation value of X. So this, which I can plug it into the second equation that I have written here for density matrix, from which we can reconstruct the final state that we want. Let us look at one last important final thing, which is quantum Fourier transform. So most of you who have already worked on Fourier transforms, you know that Fourier transforms are something very key and important, and you would have used it in multiple occasions for different fields. So the usual discrete Fourier transform has a kernel such as this. So you have f of k, which is basically a multiplication of the value that we need times a kernel, exponential kernel, which does the Fourier transform of the value that we need. So in a QFT, in a quantum Fourier transform, it is almost exactly the same, except that we take the quantum Fourier transforms of the probability amplitudes. But the kernel is exactly the same. Say I take the same 4 values that I showed before, alpha I, which are I, 2 plus I, root 2 I, and 1, and I want to compute the discrete Fourier transform of this. If we plug it into the first discrete Fourier transform equation as shown there, f of k, I will get the outputs as these 4 values. You can work this out manually on pen and paper. But when I ran the quantum Fourier transform code on IBM-Q, which is based on a quantum circuit, which looks like this, I get these 4 values, which are almost exactly the same as I would have done on pen and paper on a classical machine. This, I think, is something extremely wonderful, because now just imagine that I'm asking individual superconducting transmons or electrons to do Fourier transform for me. I think we are in an era in physics where computation has become something more physical than ever, right? But note, one very important thing is doing a quantum Fourier transform is exponentially faster compared to the normal Fourier transform that we do on our normal computers. I think this is something extraordinary, right? Because we are getting exponential speed up. Similarly, we have other kind of quantum computers called as quantum annealers. If you are familiar with what is known as Monte Carlo or quantum thermal simulated annealing, if you have an energy landscape, it can be a cost function, it can be I don't know, the money expense that you have had over the last few months or whatever. So there were peaks and dips. And if you want to optimize and see which was the minima or maxima, one thing what we do is we go from one minima to the other to find which is the global minima or the maximum, right? Here, for instance, I've taken the energy landscape of a quantum object or a chemical molecule, for example. If you want to know what is the ground state of a system, you will have to know what is the least energy of the system. The usual way would be to go from minima to minima, searching each minima. But using quantum computing or quantum mechanics, concepts of quantum mechanics, you can tunnel from one minima to the other using the concept of quantum tunneling. So now this lets you go from minimas to minimas very easily. So this also could be used to do things like optimization, which many companies like D-Wave and etc. are already using to do finance problems, etc. If you see at what are the current computers that we have right now, we have several companies like IBM, Google, Microsoft, Rigetti, etc. Each of them, as you see here, have their own physical manifestation of quantum of qubits. They use, some people use superconductors, some people use photons, etc. And each of them have their own coding language. They have their own coding to the underlying platform conversion languages. And they're investing in millions and billions because the key idea is the advantage that one would get in computing by the spatial complexity, that is how much data you can store and how fast you can do computing, that is doing computational tasks. It might be numerical things, addition, subtraction, whatsoever, right? Even things like Fourier transform. The key thing to note is that quantum computers are not here to replace every possible thing that we do on classical computers, but there are certain operations such as factorizing numbers into different prime numbers, or it might be finding an object in a haystack, things like that, right? It might be a simple search algorithm, it might be a sort algorithm. So how fast can we do this as compared to the computers that we have right now? So these on quantum computers have almost either quadratic speed up or it has exponential speed up, which makes things very lucrative for everybody to explore this direction and even companies to invest. And note that all of this is possible only because of the rules of quantum mechanics, which has changed the way we look at computation in general. So for example, if I take a 54 qubit IBM Q machine, which is there now, I can compute 2 to the 54, that is 10 to the 16 Fourier transforms exponential faster. It is a huge number. If I have to do direct numerical simulations on discretization, such as a grid of 10 to the 5 cubes, so that is 10 to the 5 discretization points on X, Y, and Z, which is a huge number, what we can do on a quantum computer. As I told, they show exponential speed up at most, or super polynomial. And as I said, every qubit can store two values. If I have one qubit, I can always write them as a superposition of C1 ket 0 plus C2 ket 1. So you have now two spaces to store C1 and C2 with just one qubit. And imagine this thing grows exponentially, 2 to the n, right? If I have n qubits, I have 2 to the n values that I can store, right? So in terms of space complexity, you save as well. There are certain difficulties because quantum computing or quantum mechanics in general functions at very low temperatures, right? So there are cooling issues, just like Sitara was mentioning, there are cooling issues. For example, the one here in New York, Yorktown Heights, the IBM Q machine, or many other superconducting quantum computers are maintained at probably less than a few millikelvin, which is probably one of the most coldest points on Earth, right? So, which needs a lot of energy and cooling and all of this, which is certainly something we need to work on if we need to invest on bigger manufacturing of quantum computers. And also, quantum algorithms are something different by itself. They're not like the usual codes that we write on classical computers. You need to use the rules of quantum mechanics to develop new algorithms. So we need to work more on that. And currently, I think it's a good idea that if we can use all three, that is our CPUs, quantum processing units, and GPUs together to see if we can achieve greater heights in computation. For example, quantum turbulence or quantum fluid, which is quantum by nature itself, is something interesting to study to start with, right? Because the object is quantum and you're using a quantum-based machine. It's good to start from those points. So in general, it might be direct numerical simulations of turbulence or Navier-Stokes, which I study, or it can be any other fluid dynamical system, which I think would make a huge difference in probably a decade or two to come, where we will see much better simulations, much higher, with higher computational complexity speed ups, which will let us understand physical systems much better than we currently do. So most of the new results that we did and an overview of all the things that I have talked so far were in these two papers. One is the one we wrote recently, and another technical report by NASA recently that was published. So with this, I think I'll end my talk. Thank you very much. So the main idea was that to motivate something together, that is something more fundamental, such as entanglement, which is so conceptual and so fundamental by itself, and see how we can take that on to some very day-to-day aspects, such as computing in general, and see how we can use quantum mechanics to do all the tasks that we need mathematically or numerically to understand the world in a better way. So I hope it was inspiring in some way, if you could take away some points out of it. And if you are inspired to take things further and understand more, you can always ask me questions. Yes, I think I'll open the stage for questions.
Thank you so much, Sachin. That was like a very fascinating talk, and you covered such a huge, bandwidth of different topics. So thanks a lot. That was great. We can take maybe 2 or 3 questions because you've been talking for a while, so we don't want to push it too much. Yeah, anybody, you can just unmute and ask. So there are a few conceptual questions that we had already collected. They are probably going to be... Okay, so let me start anyway. So there is one question about how electrons have the wave nature as well. And this was proved to be true, through experiments. So what does it mean, though, for an electron to have wave nature? For example, what happens to its properties like mass and charge when it interferes as a wave?
So quantum objects in general, for example, we know that they have a dual nature. So the point or the time where they manifest each of those, either as a particle or as a wave, depends on what scenario you make them face, right? For example, if there is an experiment such as diffraction or interference, based on the obstacle that is there in front of the object, quantum object, they show their wave nature, right? But in terms of, say, photons, in terms of thermoelectric emission or things like that, they show particle kind of nature. So basically, basically any quantum object fundamentally is a wave. But then the way they are a wave is that if you collect different waves of different modes and superpose them such that they are a stationary wave, right? When I say stationary wave, that their endpoints are fixed and they have one big node and one big antinode, right? So now this collection as a stationary wave of different waves that it is made of, superposed of, that entire wave as a packet, it behaves like a particle. So, but when you try to address the particle or like interact with the particle, each of the waves that it is made of has a certain phase, for instance, right? Every wave has a phase, for instance. So it is these phases which interact or which manifest the wave nature of the particle. So that is the fundamental way they're constructed in general. So that is why they can show, it is based on how you interact with these particles. They show either their particle nature or their wave nature. So that is the interesting part of the duality of quantum particles.
Right. I think such fundamental questions are always intriguing because they really challenge our understanding. So there's one question about how quantum mechanics can help in the macro world, since today's talk was mostly about applications, and what are the benefits of knowing it in, as in real life situations. But I think you covered that. And part B of the question is, does it help in cosmology, since the universe is largely dominated by big objects?
So that is a question which is a field by itself, which is quantum gravity, for instance, right? Which is true. We have massive objects in the universe. The question is, how can we unite quantum mechanics and the effects of massive objects, which is gravity, right? So that is the key, the question which physicists are currently answering, right? So the question is, how do you, we have united all the fundamental forces in nature, right? Most, except for uniting quantum mechanics with gravity. Gravity is, as we call, high energy physics. Why do we call it high energy physics? It's because gravity by itself is a very weak force. You need loads of it to get any kind of observable effect, right? Now, how do I combine these two objects of quantum mechanics and gravity? So the most important thing here is there are two factions which you might know. One is loop quantum gravity and the other is string theory. So the importance of it is certainly that we will, if we combine the notion of quantum mechanics with gravity, we will be able to understand how gravity, whether gravity could be quantized, right? And how this quantization can change the way we look at gravity in general, right? So in that sense, I think this is one of the most important questions that we need to understand or we deal with, that is understanding, applying quantum mechanics to gravity or massive cosmological objects to get quantum gravity. Yeah, so yes.
Right. I think even before the unification, though, in cosmology, if you're studying at inflationary timescales, quantum mechanics already does have a huge role to play. Yeah.
Yes. So quantum mechanics is fundamentally embedded in cosmology,
right.
But like the more recent and the most important pressing questions are like these. So yeah, very, very true.
Right. So if anybody else has a final question or maybe two, we can take that.
Hello?
Yeah.
Yes.
Yeah. In our classical logical circuit, suppose if we take OR gate, AND gate, for NOT gate. We can construct that using transistors, right? Using transistors, we can construct NOT gate.
Correct.
Now in quantum gate, how are we going to construct quantum gate? Are we going to use transistors or optical device, something like that? Because we are going to change the quantum behavior itself, right?
Correct. So if I give you an electron, if I want to make a unitary operation on it, what do you think I can use to change the state of the electron?
Like spin up, spin down, like that?
Yeah, so you can use a simple magnetic field.
Yeah, like Stern-Gerlach experiment.
Exactly.
Like
so
okay.
Those are also quantum gates, right? So you can use
okay.
a combination of electric fields, magnetic fields, or in terms of, it might be polarizations in terms of photonics and things like that. There are physical interpretations or physical ways in which you can implement a quantum gate, right? So if you want to flip a state, you can just do a population inversion. For example, if you have all the states occupying state 1 of a 2-level system, if you can shine electromagnetic waves and do a population inversion to the other state, or if you want to excite the state to a state 1, that is a simple NOT gate, right? A simple NOT gate, as I showed, was just a flipping between 0 to 1. All that you have to do is shine light on an electron which is in the ground state and make it go to the first excited state. Right? So that is a simple NOT gate.
Yes. Okay, thank you.
Anybody else? Actually, Chakradhar sir had noted down a question.
Okay.
How does quantization behave in a singularity?
How does quantization behave in
a singularity? And before that, he also asked, does quantization hold true for space and time? And if yes, how?
Oh, about the first question, I'm not too sure of what the answer is, because I don't, I'm not an expert at that. But I could certainly say that loop quantum gravity, for instance, or singularity or string theory addresses these two questions which you asked, that is quantization of space and time, right? So it's about what are the smallest distances that one can think of quantum mechanically, or how you can discretize space and time. So there have been many efforts. For example, people have tried to talk about something called chronons, which are quantas of time, these things are not established results. These are not established ideas in general. But yes, so the idea of quantum gravity, that is loop quantum gravity, for instance, is to look at whether we can quantize the space and time as we know, right? So which is the key interest. That is the reason why we want to apply quantum mechanics to gravity, to understand if we can discretize or if we can quantize space and time. String theory, on the other hand, takes a little different approach. It sees the world as made up of strings, and each of the fundamental particles to be as an outcome of the different eigenmode vibrations of these strings that we have, right? So that is a different quantization picture of the universe as string theory sees. But on loop quantum gravity, this is what they try to do. So if we can quantize gravity or successfully as a complete theory, that would be a complete theory of quantum gravity.
Okay. Two personal questions for you. One is, since you've studied loop quantum gravity, and since there's a conflict between string theory and that, do you personally support one of the theories more than the other?
Well, that's a...
If I'm putting you in a spot, you can choose.
So I would rather say that both are potentially strong theories.
Okay.
But since I come more from a general theory of relativity background, I would tend to have a soft corner for loop quantum gravity. But yeah, I think both are extraordinary theories.
Okay. Thank you for that. And finally, we've had a lot of technical questions. So I wanted to personally ask you, number one, what is the biggest challenge you face in this really modern frontier of studying quantum computing, as well as figuring out fluid dynamics in this new context? So maybe you can address the challenges as a student or as a researcher as well.
So the problems is it's basically that we don't have enough quantum algorithms. We don't have enough machinery. Like for instance, I can't always get hold of a quantum computer at hand to run my codes, for instance. But in general, setting up a classical problem in terms of a quantum in terms of a quantum language is inherently difficult, because I have to convert everything such that it is amenable to be solving on a quantum language. So this is the key thing. So, but the key thing is to develop better algorithms, just like we have numerable algorithms in computer science for so many operations, right? Similarly, we need algorithms in quantum computing, which can solve different things, which is the first key step. Obviously, getting hold of quantum computer is more often just like I can have a PC at home. We are far away from that, but that also matters. Yeah, so I think these are some key important things that I would face in general about solving these things.
Okay. Cool. So final question for you is, as you can see here, Naxxatra has kind of interacted with maybe 1,000+ students who are all aspiring researchers or either in science or technology domains over the last just, 6 or 7 months. So, and a lot of us are engineers wanting to transition into science, pure science. So first of all, what is your advice for that? And in a more general context, what do you think really makes a good researcher? What do you think are general principles we all can follow to be able to learn better and do better research?
Okay, so even when I started engineering, I think I was always interested in physics. So the key idea is that never to let curiosity die, point number one. No matter how fundamental the question is, go ram at it. This is what I would say. So the main thing is whatever field you choose, it might be physics or chemistry or whatever. I think addressing or having the courage to address even the fundamental questions is the key thing it's about thinking first what is important for the field itself, or if the society at large. Second is, what are the fundamental questions if I answer that can help me do that? So the way I did it was, when I did my engineering, I also did physics and math in the side, right? So I tried to keep both balanced, because I knew that as important as getting engineering done in the real world, it is also important to address fundamental questions and foundational questions. And if you try to maintain that balance, I think that is what will make us always have a foot even in science. So it's about not letting even small loose ends, for example, this might not matter to the world, a question like that, because it belongs to foundational science. If you ignore something like that, then probably it's hard to transition. But even when you give importance even to such small things, I think that's how you can transition. And I think it is completely open whether you do engineering or not. Even after engineering, you can always transition to science. You can always take that step. Reading good books in physics or math or whatever, and quality discussions, I think, would help. That's what helped me when I was at CFRCE, for instance. Yeah, I think as researchers, I think the most important thing is to stay true to every result that you get. That is, actually be sincere in answering every question that you have, no matter how hard it is. I think that is what makes one a really good researcher. You go at it, you ask questions, you go beyond the question you asked, and every small result or step that you write, I think one should be very sincere in trying to understand the physics that we're trying to do. And I think that's the most important trait as a researcher, to appreciate every tiny detail.
Right. Thank you. That's really inspiring. I think especially just the message of attention to detail is kind of lost in the sea of information we get today. So, and yeah, this really is a great boost for a lot of people we've met who are from the engineering background and are trying really hard to make that transition. So I'm hoping that this will help, and some of you from YouTube, wherever you're watching it, you have the hope and the inspiration to just make that leap and, I guess, work hard on it. So on that note, I guess we'll end. Do you have anything else to say, Sachin?
So first of all, I thank you for this, for letting me be with you guys. It was wonderful. It was a wonderful time that I spent. I could discuss. I got really interesting questions. I think it was a fresh breath of air talking with all of you amidst this situation. And I think stay true to the research that you do. Do it with all the zeal that you have, that you want. And yeah, that's it, I think.
Okay, thank you so much. And yeah, I think in the middle of a pandemic, having this community and such interactions is so great.
Very
yeah. So on a final note, if you guys are watching on YouTube, you can apply for Naxxatra's upcoming opportunities. I've left some of the links in the description. So whether you want to work on a collaborative project, the current topic is Cepheid variable stars. We also teach you guys how to do data analysis and things like that. If you're not that great at programming, we also have a programming course coming. So just let us know or apply directly, and we are always here to support you in whatever academic journey you can. We have a pretty good, large pool of mentors right now, so we can give you all the support that is possible. So, and thank you for watching. Thank you so much, Sachin, for joining us.
Thank you so much.
Amazing. Yeah.
Thank you so much.
Good night, everybody.
All right. Thank you. Take care.